subsequent lectures. So it would be good if you go through these videos and then come and attend the session. It will be more value adding to you so that you are thorough with the concepts. You hear it already in the video and then come and listen. And then you can obviously fast forward videos wherever you feel confident and then have a relook at certain portions if you wanted more clarifications. So last day, we just had a quick discussion on what is an instruction pipeline in a RISC microprocessor. We are taking a case study and we found that we are following a 5-stage RISC pipeline. And the 5 stages are IF, instruction fetch, ID, instruction decode and register read, EX for execution and address computation, MEM is for memory access, and WB is for writing back into registers. And then we have seen that what are the operations done for, let's say, for ALU instructions, for load and store instruction, and obviously for a branch instruction. Towards the end of the session, we just had a quick review on what are the issues that we expect in a pipeline, what is our idealistic assumption, and how actually it is happening in a pipeline. So today we are going to talk about pipeline hazards. That's where we stopped yesterday. Just hold on for a second. Okay, so we are now going to learn about instruction pipeline. So this is what we are going to do. Let me share my slide. Can you see the slide in full screen mode?
Yes, sir.
Okay. So we will talk about pipeline hazards today. Okay, so this is what we have learned yesterday. What is the pipeline risk data path, where the instruction execution is further subdivided into 5 subcomponents known as instruction fetch, instruction decode, execute, memory access, and the write back operations. Now, these are the steps what we discussed, and then we know that every cycle a new instruction is being fetched. That's what you see here at the clock cycle number 1. The first instruction is fetched, second instruction is fetched. So every cycle we are fetching a new instruction, and under the ideal scenario, every cycle one instruction is reaching back the W back stage. So if you vertically look into, then you can see that for clock cycle number 5 onwards, you will see the write back stage is busy, the MEM stage is busy, the EX stage is busy, the ID, IF, all stages are busy, but they are rather busy with different instructions. So there are certain limits to pipeline. We will try to see that. Circumstances that would cause incorrect execution if the next instruction is fetched and executed, that is being known as hazard. So hazards are not, pipeline hazards are not techniques. They are scenario which could cause an incorrect execution if the next instruction is fetched and executed. So we know that every cycle you can fetch a new instruction, and in the subsequent cycle it goes to ID, then the very next instruction it goes EX. So for each instruction we basically assign 5 continuous clock cycles right from the fetching up to the WB. Now, for certain scenarios, if you stick on to this, that means if you fetch and if you decode in the assigned time slot, it would cause an incorrect execution. Circumstances that would cause incorrect execution if the next instruction is fetched and executed, and that is what is known as a hazards. Now, there are three different types of hazards. The first one is known as a structural hazard. So when you have different instruction at different stages in the pipeline, but they basically wanted to make use of the same hardware resource, then that result in a structural hazard. So imagine, let's say you have two instruction I1 and I9, let's say two instruction, but in a given clock cycle, I1 and I9 are going to use the same resource. It can be a register, it can be a memory, let's say it can be a floating point unit, something like that. So at the given time, a resource cannot be used by more than one instruction. It is as good as like I am going to ask you, can you read page number 10 from a book? At the same time, can you read the contents of page number 20 from the same book? So the book is the resource, and I wanted to read the contents of page number 10 and 20 together. That is impossible. So such kind of scenario happen in pipeline also, and that is what is known as a structural hazard. The second category is known as a data hazard. If an instruction in the pipeline requires data to be computed by a previous instruction which is still in the pipeline, then we call it as a data hazard. So the idea is, let us say you have I1 and I2. I1 is going to produce a result. Let's say we call it as X. And I2 is going to use this X. So I2 is going to produce some result called Y. But Y can be produced only if the result of X is available. So I1, if it is a store instruction, then the effect of store is reflected in the memory location, in the mem stage. Or if you are going to write into a register, then the value of X will be available in the register only at the WB stage. That means, as far as I1 is concerned, if the result is to be reflected in memory, at least you have to wait till mem stage to over. Or if the result is to be reflected in a register, you have to wait up to the WB stage. Now imagine, let us say you are going to make use of this result, whatever is written. For example, I'm going to write some result by I1, and that result has to be read by I2. So this result produced by I1 acts as the source operand to I2. So I2, normally what happens if you have clock cycles 1, 2, 3, 4 like that, if this is going to be IF, and at clock cycle 5, I am going to perform write back. Now for I2, what happens is I2 is going to fetches I2, and you are going to perform an ID at clock cycle number 3. So it is at the ID stage I read the register operands also, but my value will be available only at clock cycle number 5. That means the first instruction will produce the result only at clock cycle 5. The second instruction wanted to use the result little early, and then that is going to create a problem, because I am going to use the result earlier than what is then expected. So there exists a dependency between your I2 to I1. And if you permit I2 to execute in its assigned time order, then that is going to create a problem. So an instruction in the pipeline requires the data to be computed by a previous instruction in the pipeline. So if you run the second instruction in the assigned time slot, it can cause an incorrect execution. That is why it is known as a data hazard. Now the third type of hazard is known as a control hazard. If a succeeding instruction put into the pipeline depends on the outcome of a previous branch instruction already in the pipeline. So let us say you have I1 and I2. I1 is a branch instruction. So if the branch is taken, then it will be going to I7, for example, 7th instruction. But the branch is not happening, then it will come into I2. So we will come to know whether a branch is happening or not only after few cycles after fetching I1. I have to perform a decoding. Only during the execution stage, you will come to know whether a branch is happening. So by that time, I have to fetch something. So normally what happens, whenever one instruction is fetched, as per program counter updation, I am going to fetch I2. So while I1 is in the decode and execution stage, I2 is already fetched. So the succeeding instruction, whether I2 should be executed or I2 is an instruction that is a must execute, we will be knowing it only after the outcome of the previous branch instruction is known. So in this case, I'm not sure whether I2 is a required instruction until the outcome of I1 is available. So without waiting for I1, if I fetch, decode, and execute I2, then that can cause an incorrect execution, what I've already mentioned. So that is known as a control hazard. So we have three types of hazard as mentioned. Structural hazard, where different instruction in different stages of a pipeline wanted to use the same hardware resource. So it's basically a hardware resource conflict. One hardware resource demanded by multiple then instructions. Data hazard means there exists a data dependency between a previous instruction. So until the previous instruction is not over, I cannot continue with the current instruction. And the third one is, I'm not sure whether this current instruction is to be executed or not because it depends on the outcome of a previous branch. Now let us deal each one of them separately. We will try to learn about structural hazards. Okay. So in structural hazard, consider the case that you have a uniport memory. So uniport memory means accessing memory, I have only one port. So if this is going to be your memory, there is a read and a write port that you have. So any access to memory has to be happening through this. So how do you do it? You have an address bus that is coming into the memory, and from this you are going to give back the data through the data bus. So consider you have a load instruction. So load instruction is going to perform fetching, then decode and reading of the register. So you got the base register value and the immediate value. You add them together. So the effective address is obtained. Based on the effective address, you are trying to go to the memory location, fetch the contents and put in the register. That's how load is over. Now imagine you have a next instruction that is going to come. So I don't bother about what is the instruction. Let's say it's an add instruction. And there is another instruction. Now consider this point. So here what happens is, at clock cycle number 4, you have your load instruction accessing the memory. At the same time, you have instruction 3 also accessing the memory. But instruction 3 is accessing memory to perform instruction fetch. I wanted to fetch an instruction, whereas load is accessing the memory in order to access the data. So one is in the mem stage, other one is in the IF stage, but both are accessing memory. So if your memory has only one port, then this becomes a hazard. A memory cannot retrieve that two operands at the same time. So this scenario is known as a structural hazard if you have only one read port in the memory. Now, how do you resolve structural hazard? The simple and straightforward solution is eliminate the use of the same hardware for two different things at the same time. So what is that what you are going to do? So the first approach is you have to wait. So whenever you find that two instruction is going to use the same hardware exactly at the same time, first of all, you have to detect that this is going to cause a hazard, and then you should have a mechanism to stall. So one of the instruction will be asked or will be delayed. They cannot run at the same time. So you have to find out there exists a presence of a hazard, and then find out one instruction, and we have to delay that instruction such that they both are not going to be performing the operation at this time. The second one is known as going to be a duplicating a hardware. So duplicating hardware means multiple such units will help both the instruction to progress. So let me draw your attention to an example of the structural hazard. So imagine the case, there is a mother and there is a small baby. There are two children, one is very small and the other one, let's say school going kid, a nursery school going kid. So what happens is, let us say one time the mother may have to help the elder kid in doing the homework. At the same time, the younger kid is also asking for some food. So two different instruction or two different entities, the younger kid and the elder kid, they want the same resource. That is, a mother is a common resource. They wanted the service of the same resource exactly at the same time. And that is this is a structural hazard because there is only one resource and two of them wanted at the exactly same time. So one approach the mother can use is known as the wait mechanism, where the mother will tell one of this entity to wait. So it can tell the elder kid, you will wait, I will first feed the younger one and then I'll come and help in your homework. So first of all, the mother, there should be mechanism to detect that there exists a hazard, and then you have a mechanism to stall. Stall means you are asking them to be idle for 1 or 2 clock cycles. The second one can be duplication of hardware. So what the mother can do is mother can employ someone else. Let's say there is a maid at home. So the mother can tell the maid, can you feed the younger one so that I can concentrate on the elder one? Or the mother can ask the father or some other member in the family, can someone help the elder one in doing the homework such that I can concentrate on the younger one? So in the second approach, we are not waiting for anyone or we are not delaying any one of them, but when we are actually trying to have a duplication mechanism. So this duplication mechanism, by virtue of that, no one is waiting, but I am adding more resource such that this duplication mechanism will effectively work. So now let us try for the first approach, that is the waiting approach. So you have a load instruction what mentioned. So for the load instruction, I'm going to access memory in cycle number 1 for instruction fetch and cycle number 4 for accessing the memory. So subsequently this is coming. Now I know that a new instruction is going to be fetched and that is going to clash with that. So I am not going to fetch the instruction 3. So ideally your instruction 3 was supposed to be in this slot. Now I am not permitting because it is going to create a stall. So we call it as a bubble. Bubble means it's a no operation. That means a pipeline register will be filled with fully zeros. That means in subsequent stages also you don't do any operation. So ideally in clock cycle number 7, one instruction is getting over. So clock cycle number 8 also, there should be a write back stage for one register, but that won't happen. So clock cycle number 7, there is a write back for instruction 2, and the instruction 3 will write back only at clock cycle number 9. So that is what is going to be the mechanism by which you introduce a stall. So stalling or adding bubble is nothing but creating a no operation. That means for that particular cycle, my IF will not do. The very next cycle, ID will not do any operation. So incurring a forced delay, that is known as bubbling or stalling the instruction. Now the second approach is at the design level. I told that the problem happened in the previous case because I am having a memory access at clock cycle number 4 for the load instruction and a new instruction that is to be fetched. This can be avoided if the IF stage and the MEM stage are going to access two separate memories. That means two separate read-write ports. So that can be facilitated, and this is what is known as a split cache. So generally, rather than imagining your cache memory is a single unit, I can have one cache separately for storing instruction. So all my IF operations will happen from this cache. And then you have another cache which is touched during the MEM stage only, and that is what is known as data cache. So if you look at the specification of laptops or cell phones, you can see 8 KB L1I cache and 16 KB L1D cache. So this separation is happening in order to eliminate the structural hazard. So you have different levels of cache. We will learn about them. So we have a processor, plus you have an L1 cache and L2 cache. So like that, you have your main memory coming. In all these places, there is no separation for instruction and data. Whereas in L1 cache, you keep your instruction and the data are two separate caches. That is why we call it as a split cache. Whereas when you come to L2 or other levels of memory, we don't have any such logical separation for instruction and data. So you call them as unified cache. So one way, like this is a very important question that typically in the previous years also, when Intel came for campus recruitment, some of your senior students give us this feedback that this question was asked, why your L1 cache is split, whereas your L2 cache is a unified cache. It is not related to any cache memory properties. It is related to the structural hazard issue of the instruction pipeline. So instruction pipeline is going to interact or going to touch only my L1 cache. And there are scenarios where IF and MEM has to happen together. So there is a separate dedicated line from processor to D cache, which is bidirectional. and there is a dedicated line from iCache to the processor that is unidirectional, because processor is not going to write anything into iCache. It's always reading from the iCache instruction fetch. Whereas when it comes to data cache, you have transitions in both the direction. When it is a load operation, it is from the data cache to the processor. If it is a store operation, it is from processor to the data cache. So data cache access from processor is actually bidirectional. There are two approaches that we discuss now. The first approach is introducing a stall. In that case, one of the instruction is penalized. It has to wait. And second approach is having a separate cache memory for this. So before going to data hazard, let me see if any student is having any query in this portion. So we have to understand these are the concepts we learned now. First is we need to know that there are some scenarios in which your instruction execution won't happen in the assigned time slot. If you do that, that can result in some kind of an error that is known as a hazard. And after that, we are learning to understand what is a structural hazard and how can you mitigate that. Any questions?
Excuse me, sir.
Yeah, yes, go ahead.
Sir, this second method of fixing structural hazard, can you please explain it again?
Yeah, okay. So structural hazard means when you have one resource and two people are more than two or more instructions are trying to use a resource, that is known as a structural hazard. So traditionally we were talking about the IF stage and MEM stage. They are using memory because I have to access something from memory. So how do you access something from memory? You give an address and memory will respond back with the content of the address to location, right? So if IF and MEM, both what are they doing? I give an address and both has to be supplied with, and if it is an IF, I have to return the content specified by that to the instruction fetch unit. If it is a MEM stage, whatever is the address given, if it is a load operation, I may have to return the corresponding word. So there is a bus conflict because if processor is connecting to one bus and all of them, your instruction and data is stored in one cache, maybe different locations, but the connecting point is still one. You have only one data bus. So that was the hazard. And how do you eliminate it? By duplicating it, by having two separate caches, one exclusively for instruction, other one exclusively for data. So from processor, there is one bus connecting to the instruction cache. So during your instruction fetch stage, I go and read only the iCache. At the same time, I can perform a mem operation for a previous instruction because your data cache is connected to processor using a separate bus. In that way, the hazard, because now there is no two instruction trying to access the same resource because I duplicated the resource. So one instruction will access iCache, one instruction will access the Dcache. Is that clear, Narmin?
Yes, sir. Yes, sir.
Okay.
Understood. Thank you, sir.
Any other query? So understanding these pipeline hazards are very important. Next to 4 to 5 lectures, this concept has to be thoroughly known in order to appreciate the rest of the pipelining. Okay. So if there is no other query, I will go to the subsequent slides. Now we come to data hazard. So consider this piece of code that is being written. So they all are ALU instruction. It can perform arithmetic as well as logical operation. You can see that it's add, sum, and, or, and XOR. The last three are logical operations. The first two are arithmetic operations. And the general format that we follow in a MIPS architecture is, so here you have R1 is going to be your destination and R2 and R3 are going to be source. So the meaning is content of R2 and R3 has to be added and then the result has to be stored in R1. So everywhere this is going to be the pattern as far as an ALU instruction is concerned. So when I talk about ALU instruction, and since it is a load store architecture, RISC architecture, the destination operand and both the source operand has to be registers. I cannot perform any ALU operation on outside a register. So first I have to make sure that the appropriate operands has to be kept in R2 and R3. And then I call the instruction add R1, R2, R3. So R2 and R3 would be read and then you're going to do it. So what happens? I fetch the instruction and I will decode, I come to know it's an add operation, and R2 and R3 are the source operand. So the content of R2 and content of R3 both will be read in the RF stage itself, and then your R2 content will come through this leg and R3 content will come through this leg, and in ALU I am going to add them. The result is going to be kept in this pipeline register. Since it is a ALU operation, nothing is done in the data memory stage. So whatever is the content in this pipeline register, it gets copied to the next pipeline register at the end of one cycle delay, and I'm going to write back into R1 in the WB stage. So this is your clock cycles, let's say 1, 2, 3, 4, and 5. Now, let us see the next instruction. It's a sub instruction, sub R4, R1, and R3. What does it mean? My source operands are R1 and R3. So R3 content anyway I have, but I'm going to read the content of R1. R1 is a register file. If I go and read the content of R1, this R1 and R3 has to be read in this particular clock cycle number 3. So I fetch the instruction, perform decoding. After decoding, I will read the source registers also. So ideally, I read from R1. So R1 has some contents, but whatever content I'm reading from R1, that is not what is intended in this program, because here, as per the programmer's view, it is this R1. So the result of the first add instruction has to be used in the next one. So if I read R1 and I proceed into ALU in its assigned slot, because my operands are there, I do R1 plus R3, then I'm going to store the result. So I'm going to store in R4 in the assigned time slot. Whatever result I store in R4, it is going to create an error. So there is nothing wrong as far as the program is concerned, because then the pipeline has to understand that there exists a dependency. So, but the actual content of R1 will be available in R1 only at clock cycle number 5, and I am going to read the value of R1 at clock cycle number 3. So if I read the value of R1 at clock cycle number 3, it is going to be a wrong data. Similarly, if I go to the third instruction, that is going to perform an instruction fetch, and here also I am going to read the content of R1. So R1 is read before it is updated. So this, if I continue the execution in the assigned time slot, then that is going to give me a wrong value in R6. Similarly, this also is a problem, because I'm going to write into R1 and exactly at the same cycle, but I have to make sure that this writing happens. That's why I have put a red color in this R1. This shows the dependency. So the second instruction is dependent on the first one. Third is dependent on the first one. Fourth is also dependent on the first one. But if you look at the fifth instruction, that is the XOR instruction, one of the operand is R11 that is available. By this time, whenever I'm going to read R1, that happens at the clock cycle number 6. This is the updated R1 that I get. So any reading of R1 after clock cycle 5 is going to be the correct data. So the value that is read by the sub instruction and an OR instruction, they are going to be wrong data of R1. Even though I read from R1, that is not what I want. So this scenario is known as data hazard. If I continue my execution without addressing this, it leads to an incorrect result. So there are 3 generic data hazards. So the first one is known as read after write hazard, which is also known as a row hazard. So consider 2 instruction I and J that is been given. So instruction I is going to be add R1, R2, R3, and instruction J is going to be sub R4, R1, R3, and there exists the R1 where I'm going to write the result, and here I'm going to read the result. This is known as a row hazard, because I have to read a data after the writing is over. So instruction J try to read an operand before instruction I writes it, then that is what is known as a row hazard. So instruction J normally will read R1 before instruction I completes writing in R1, and that is why the name row. This is actually caused by a data dependence. There exists a dependency from I to J. This hazard results from an actual need for communication. So it's not only about the name of the registers. Actually, instruction J is dependent on the outcome of instruction J I. So J cannot run in its assigned time slot. Okay. Now, the second category of data hazard is known as a write after read hazard. So, if instruction J, that is the second instruction, writes operand before instruction I reads it. So, consider this scenario. You have I and J. I'm talking about R1. So, in this case, when I talk about R1, what happens is so this is the generic hazard. Okay. So you have an instruction I where it is going to read a value from R1 and instruction J is going to write an instruction into R1. If instruction J happens to write into R1 before instruction I going to read it, which generally won't happen because this reading happens in clock cycle number 2 and this writing happens in clock cycle number 6. Why 6? Because J is starting only clock cycle number 2. So 2, 3, 4, 5, 6. 6 is the write back. But so far our assumption was if instruction I is stalled, then instruction. What if my subtractor is not free? So instruction I is going to be blocked. Will I permit instruction J? That is called out of order execution. So in order execution means I will start executing J only after execution of I is over. If by some reason, for example, if the subtractor unit is not available or value of R3 not available, something like that, if that is a scenario, if I execution of I is somehow delayed and if J is permitted to execute, that means instruction J write operand before instruction I reads it. That is what is known as a war hazard. This happens because of the same name. There is no transfer of data from R1 to R2. We have to make sure that there is no transfer of data coming from J to I. That should not happen. Ideally, in the program sequence, there is nothing. So what this K wants is there exists a raw hazard between J and K. This R1 is same. Whatever is the result of J, it has to be used by K. So if this would have been R5, this also can be R5. This is same, but these two are not same. Only the name is similar. So this is known as anti-dependence by compiler writers. This results from the reuse of the name R1. And this cannot happen in a MIPS 5-stage instruction pipeline because in pipe all instruction take 5. Read always happen in stage 2 and writes are always happening in stage 5. That is a scenario war hazard will not happen. But if at all you permit, all instructions are not 5-stage. There are some instructions which will take more than 5 that we will learn later. In that case, and I am permitting out of order execution. Out of order execution, if I permit, it's called OOO. If triple O execution, if you permit, then there is a possibility that J can run before I. In that case, if you do that, then your K is going to read with a wrong result. Such kind of scenarios should not happen. So ideally, the thing here is there exists a raw hazard or a data dependency between J and K, but ideally there is no dependency between I and J. It's only the name that is similarity. So compiler should not have used the term R1 here. It should have used some R6, and this also can be R6. So that even if J runs before I, as long as it is R6 and K runs after J, the issue is settled. But anyway, we are keeping this kind of a hazard for a later discussion because right after read hazard, we will discuss about when you talk about out of order pipelines. Now, the third category of hazard is known as a WAV hazard, write after write hazard. So instruction J writes operand before instruction I write it. So consider two instructions, I and J. See the peculiarity, I is writing to R1 and J is also writing to R1. What happens? And then what happens to K? This K is going to read from R1. As per the program logic, it is written that K has to read that R1 which is updated by J. So this is the dependency as per the program sequence. What if J completes before I and I is going to write in? So J will write into R1. Later, if I completes after J, I is going to update this R1 with a new R1. Then K is going to read the result of I, which is not correct. So if instruction J writes operand before instruction I writes it, that is known as a write after write hazard. This is also known as output dependence. This also results from the reuse of the name R1. See, here you can see that the term R1 is used. Had it been R6, then these both are R1. So even if J completes before I, nothing is going to, because the moment I overwrite R1, so here I compute something into R1, later J is going to overwrite on it. So the R1 value is never used anywhere. This R1 value is never used anywhere as long as there is no instruction in between them. So if compiler can carefully or intelligently reuse the names R1 or give name to registers carefully, then this kind of scenarios can be avoided. But nothing will work as far as a row hazard is concerned. There exists an actual data dependency, and war and wow hazards happen because of the register. So by appropriately renaming the register, we can get things done. This also can happen in the MIPS 5-stage pipeline process, because all instructions take 5 stages and writes always happen in stage 5. But war and wow hazard happen in the out of order pipelines. Now, how to handle data hazard? So data hazard means an instruction need data from the result of a previous instruction. So for the time being, we are only going to handle row hazards. The other two are not to be handled today. We will deal it as and when such a kind of a scenario happens. Now think of a case that, let us say I have two instructions, add R1, R2 and R3, and the next one is sub R4, R1, R5. So what happens here is, here I am going to compute as R1 equal to R2 plus R3, and here it is R4 equal to R1 plus R5. So what I need here is, this is the R1 is the criteria. Only if R1 is produced by the add instruction, then only the subtraction instruction can proceed. Now the question is, do you really need R1? Actually, we don't want R1. We only want the result of R2 plus R3. And where is the result of R2 plus R3 available? R2 plus R3 is available in this pipeline register. The pipeline register after EX, that will store the result of R2 plus R3. And subsequently, that is going to be returned to R1 in the WB stage. So what happens? Here, I am not really interested in R1. If R1 value is not updated, but the value to be returned to R1, that is R2 plus R3, that is available here. And that is required not at the ID stage. I want this value only at the EX stage when I'm going to really perform. So can I do this? From the output of the execution unit, can you forward the result to the input of the execution unit such that R5 will come normally and this R2 plus R3 value will come from the output of the EX. So these two EX units are the same. It's not different one. This is known as operand forwarding or data forwarding. So from output of EX unit, I'm forwarding to the input of EX unit. So look at the scenario, the same example where we identified this. So add R1, R2 and R3. R2 plus R3 is what I want. So R1 will be written only at the write back stage. R2 plus R3, I forward from output of ALU to the input of ALU. So R3 will come directly through this, and here I am getting the result. So I can easily do it. So even though at the register read state, I am not able to read the value of R1, there should be some appropriate control signal which will tell R1 value will join you as and when you start working in ALU. Here is R3. So R3 is forwarded and an indication is given. R1 you have to take from the output of ALU. So from output of ALU, I am giving to the input of ALU. So this will run. The subtraction instruction can run in an assigned time slot without any delay by enabling the operand forwarding. Now, how do you handle this? You know that because it is an ALU instruction, this value gets copied to this register. Now from there, I can forward to the ALU. That means whatever was the result produced by the ALU, now it is in the output of the MEM stage. From there, I will forward to the input. So sometimes from ALU's output, you have to forward to the ALU's input. Sometimes from the output of the MEM stage, you forward to the ALU's input. And the last one is carried because we know that this writing into register happen in the first half of a clock cycle, and reading into the, you can see from the blue color. So this stands for decoding and this stands for, the blue color indicates register read operation. Whereas in the write back stage, the blue color indicates the register write operation. So when you consider a clock cycle, if this is a clock cycle what I have, your register write happen in the rising edge of a clock and register read happens in the falling edge of a clock. So if I write the value of R1 at this point, I can read it exactly from the same cycle. That is forwarding from register output to register's input. And the XOR instruction was not having any issue without operand forwarding also. This is one. So how do the circuit looks like? This is how the hardware forwarding works. You have the ID stage where I read the content of register. You have ALU, and sometimes to the input of ALU, we are passing through multiplexer. Either the value will be coming from register, or sometimes you may have to add the immediate value. So you don't know whether you should feed the register content to ALU or an immediate content to the ALU, or it is coming from next PC and all. So we learned that in operand forwarding, either we forward from the output of ALU to the input of ALU, or it can be forwarded from the output of the MEM stage to the input of ALU. So this multiplexer with appropriate control signals can determine whether this should be permitted or this or this. So out of the 4 inputs, which one should be given as the input to the ALU? Similarly, this multiplexer also take a call. So by appropriately configuring this multiplexer, so first of all, I have to understand there is a hazard, and based upon the hazard, which of the value has to be forwarded, and that will take care of operand forwarding. So operand forwarding is the technique by which the actual data, the operand is forwarded, and in the meantime, the updation happen in the real register. So before the updation happen in the real register, the data that is to be updated in the real register is forwarded. Now, even if you use operand forwarding, there is some scenario in which still there is a hazard that can occur. So consider a load instruction where 0 plus R2 is my effective address, and from there, I wanted to write the result to R1. So 0 plus R2 will be happening only in the ALU, and then value to be returned to R1 is available only at this point. But whereas in the subsequent instruction, so this is a load instruction, and there is a subsequent ALU instruction which has a data dependency with the load. So the content of the load has to be reflected in R1, and that R1 has to be used by the subtraction instruction. And where latest I want this R1, I want the R1 at the beginning of ALU. So R6 would be coming direct. So with operand forwarding, I cannot forward from here because what I have here is the effective address. Only 0 plus R2 is available here. Whereas my actual operand which subtraction instruction want will be available only at this point. I cannot forward from here to here because it is forwarding to a negative cycle. This is the end of the 4th clock cycle. The result that is obtained at the 4th clock cycle, I cannot forward to the beginning of the 3rd clock cycle. That's very difficult. So in this case, an ALU operation immediately after a load operation, even with operand forwarding, I cannot handle it. Whereas this can be handled easily because from here, my R1 is available. I can forward to the input of ALU, and here from output of register to input of the register. So what happens essentially is you have your load instruction that is coming, and then your subtract instruction gets fetched, decoded, and then you come to know that there is a hazard issue. So I will not perform the ALU at that stage. Rather, I will create a bubble, and ALU stage is delayed by 1 cycle. So my first instruction gets completed at 5. At 6, nothing is complete. The next instruction is completing at clock cycle number 7. So I am going to, that means I continue in the decode stage for 1 more clock cycle, and then only I perform an ALU operation. So once that is there, then all subsequent instructions are also stalled for 1 cycle. That means I am the AND instruction will continue in instruction fetch for 1 more cycle. I'm not going to fetch anything new, and that means the fetching of OR instruction is delayed by 1 clock cycle. So in this way, a load operation, and immediately after that, if I have an ALU operation that is going to make use of the operand in the load, then they cannot be running in the consecutive cycles. So this is what happens in this case, and we are adding a bubble to solve it. So one mechanism by which load ALU hazard is handled is with the stall. Now, can you deal with without a stall? So assume a high-level language construct that is being given. This is a very common statement that you might have used in C or C++. A equal to B plus C and D equal to E minus F. Imagine all of them are integer variables. And let us see how these values looks like. So what I basically want is, since it is a RISC architecture, in order to perform this operation A equal to B plus C, I wanted to bring the operand B and C into registers. So let me bring them. Load word. This B shows the address. So typically your B is represented as, let's say, R2, 8 of R2. That is what is known as your B. So B is nothing but an effective address. And then you load C and then you are going to add them. So RB, RC, RA, all are registers. So this is how a corresponding machine level language code looks like for the operation B plus C. And how do I store the result? I'm going to store the result in A. So these 4 instructions are going to be the replacement for A equal to B plus C. So what I'm trying to do, the operand in B that is loaded to register RB, operand in C loaded to register RC. Now RB and RC are the source operands. I generate the result in RA because it's a RISC instruction, and MIPS will use load store architecture. So all operands can to be in register only. Now what you do, whatever is available in this register RA, I'm going to store into memory location A. Similarly, I'm going to perform D equal to E minus F. So load E, load F, and then I perform a subtraction, and then you store the result. So then these 4 instructions are going to be the replacement for D equal to E minus F. Now let me draw your attention to what is wrong. So if these instructions are going to be running in the assigned time slot, let us see what happens. So wherever I have marked this red, so you have here, there is a special case of your load instruction is there, and then immediately after the load, there is going to be an add operation. So we know that in instruction pipeline, these two cannot go adjacent. There is a 1 cycle stall here. So if this gets completed at clock cycle number 5, this will get at 6. This will not happen at 7. There is a delay between them. So this will happen only at 8. Then this will happen at 9, 10, 11. This will not happen at 12. There is a delay there. So there is a delay in these 2 points because of the dependency of RC. Similar dependency of RF. And this will get over only at clock cycle number 14. Now, if a compiler, this is a beauty, when a compiler is going to go hand in hand with a processor, this is a beauty what is happening. If the compiler knows that an add and load cannot come adjacent, without changing the meaning of the program, can the compiler reschedule the code? So you have a load word, and then you are going to put it, and then you are going to have these words, and then see what happens here. All the 8 instructions are there and slightly rearranging. What I need to do is this load and the corresponding add, wherever you have this RC dependency, cannot come adjacent clock cycles. I need to have a 1 cycle gap. So can I find out another useful instruction can be put inside in between these two, but still my program meaning is not over. Similarly, I am going to put up the same scenario here because there is a load word here, RF, and there is another RF. They have to be separated. So even if I get the result of RA, I can delay storing slightly. So I am going to perform slight reorganization such that the dependent instructions are being separated. This is known as software scheduling. So the compiler, after generation of a code, you will learn about compiler in subsequent semesters. Compiler will look at the code, some kind of code analysis, and find that presence of 2 adjacent instructions like this can create a delay. Now, if you see, this will get over at 5, this will go over at 6, 7, 8, 9, 10, 11, and 12. So I could save 2 clock cycles here. At the end of clock cycle 12, the store process is over. And now let us move to the third category of hazard. We will deal more about it in the subsequent class only. This is the control hazard on branches. So what I am trying to do here is, you see the corresponding instruction that is being given. So in this, it has been mentioned, branch if equal. If R1 and R3 contents are equal, then jump to 36. You have to run this XOR instruction. If R1 and R3 are not equal, I go for AND or add instruction. This is the sequence. So if the branch is taken, that means if this condition holds, then I call that branch is taken. If the condition is not holding, then I am telling the branch is not taken. So when will I come to know? I will bring the content of R1 and R3 here. I will compare them. So only at the end of ALU stage, I come to know whether they are equal or not. But by that time, instruction located at location 14 and 18. Why this 4 gap? Because I'm going to store instruction in 4 bytes. Each instruction is 4 bytes. So instruction in 14 and instruction in 18 is already fetched. And then I take a decision by shifting into like what is a new target address. That will happen only at this stage. So this third one also is been entering. So 3 unwanted instructions entered the instruction pipeline. Actually, only this was needed. So these three, if I permit them to execute in its assigned time slot, it will lead to incorrect execution. And this scenario is known as control hazard, because before waiting for the outcome. So we will deal more about how control hazards is done in the subsequent class. So this is the conventional MIPS architecture, where your branching will happen only at the end of the fourth stage. Only this new target PC is calculated and I can go there. So I get the value of the registers are compared, and then based on the comparison, I take a call. Should I jump or not? But in the meantime, already 3 instructions are entering into the pipeline. But if you do some optimization, should I delay this branch operation, everything to the last one? We will see that in the next class. So the next class is specifically on control hazards and some techniques that are being used to handle these control hazards. That's the way how it is being done. Okay. So this is the reference material that you used. Here also that section C2 of the appendix you have to look into. So in pipeline hazards, structural hazard and data hazard is what we completed, and this is the link for the YouTube video. So let me know if there are any more queries. We have a few more minutes.